And we are back. So we're going to continue. We're continuing on. We're doing 6.2 on this lecture, but we're really you'll see it really continues on, or you should have already seen for having read it and doing the what I call it, reading assignment, that it really continues on exactly from where we left off in 6.1. So in 6.1 we left off with subsets, and you'll see that's a large majority of what we're looking at in this section is doing proofs with subsets, and doing proofs then with what do you call it? Not just with subsets, but with our other set operations in general. So let me get to one of the reading questions and we'll start there. So I gave you guys questions 1, 2, and 3 for the reading. Let's see. Well, okay, so let's answer parts of 1 here. We actually won't go through all of 1, but enough kind of stuff we need. So let's start with 1. And in 1, so you had several parts here, but what they were trying to do here is summarize. So what we'll do in this section is, in the last section, we did union, intersection, we did subset, we did set difference, but we did it with actual sets, like with concrete numbers in them, or at least, some span, some interval of numbers. So in this set, we then want to generalize these ideas, not just really generalize these ideas, but generalize the sets to any set. So the idea here is we want to start proving things about the unions, the intersections of sets, about subsets. But if we're going to prove things about those sets in general, or those operations in general, we can't use sets that just have certain numbers in them, because then whatever we prove is only true for those particular sets with those particular numbers in them, right? So those sets with numbers in them become examples. An example can't prove something in general. So we are going to try to prove now. You'll see the purpose of 1 is to get you guys prepped for the idea, and also to get you to think about these definitions that we did in 6.1. But now what we're going to do is we're going to prove things about the intersections, the kind of union and subsets of sets in general. So you'll notice every set we talk about in 6.2 has nothing defined in it. Like that's intentional. So just like we've proved, in chapter 4, we proved proofs about all even numbers or all odd numbers or all this or all that. That's what we're trying to do in this section. Is now we're going to try to prove things about all sets in general, rather than just particular sets with numbers in them. Okay, so that's kind of the idea I was trying to get to. So let's start by looking at these definitions we looked at in 6.1 in general, with general sets in 1, and then we'll get to some proofs. So 1A, to say that an element is in A, I will write this. So to say that some element is in A intersect B union C. And they wanted you to break that down. So what does that mean? Means that it is in blank and it is in blank. So notice again, the idea here is I'm not going to specify what these sets are, and it actually doesn't matter. I want to think about these sets and prove things about these sets in general. Actually the advantage is I don't want to specify anything, because I want to be able to prove that something is true about these sets, no matter what's in A, what's in B, what's in C, etc. So the key here, they're focused. Notice that they use the word and so coming from the last section, the word and, which operator for sets had and as a definition? Good, it was the intersection. So what you would have said here is that to say an element is in A intersect B union C means that it's in A and it's in, so the two fill in the blanks here would have been B union C. But the key there is the and. So the key here was to remind you that in general, an intersection means and, means it's in both of those sets. Then on, so that was part A. So then on part B, they had you focus on now A intersect B union C. Yeah, that's a big one, I think. And they what they're saying there is to say that an element is in A intersect B union C means that it's in blank or blank. So the focus there was the word or. And which of our operations are set operations? Which of our set operations corresponds to or as a definition? Good, that's union. So what we're trying to say here, what you would have said here is that my element is in A union B. Actually, we don't want that. Or it's in C. So and corresponds to intersection or corresponds to union. Now, honestly, what you're going to see in these proofs is we could break this down even farther. Well, but let me kind of leave that for the proofs actually. And then I think I know there were several other parts to this, but the only other part I want to focus on to sort of move us on to the problems I want to look at is part C here. So part C was A set difference, B intersect C. And they wanted you to interpret this here to say that an element is in this set, A set difference B intersect C, or A minus B intersect C, means that it is in blank and not in blank. So which operation did we interpret as being not only not in, but and not in? And good, that was set difference. So this, what you would say here is it is an A and not in. A and not in, B intersects C. All right. So again, my purpose with this reading, part of this was also, gave you, what do you call it? Gave you some good reminder on how we go through subset proofs, but we'll get to that on another problem. But my main purpose here was really the first three parts. To remind you, not only from last section, but really for everything you'll see in this section and the next section, that and corresponds to intersection or corresponds to union, and not in is set difference. All right, with that in mind, the second thing I wanted to sort of remind you of with these reading assignments was, so we just finished in 6.1 doing a subset proof. So I wanted to remind you of kind of how we set up and work through a subset proof. And kind of mix it in with this stuff. And so I think that I want to do this slightly out of order. Let me just look at it. Sorry, guys. Let me. Guys, all right, so I think what we'll do is, yes, I want to let's look at three. Let's do a little reverse order first. So let's look at three. So in three, I had you do a fill in the blank proof, but again, to here, three, I really want to highlight this subset operation. So intersection, union, what do I call it, a set difference. Now let's go back to the subset operation. And so the proof that they're trying to go for in three, so just to sort of write this part out, even though you have it in front of you, what we're trying to say is, and the key here, actually, before I even write that, so the key here that I really want to emphasize is we're trying to say for all sets A, comma, B, comma, C. And I even want to stop there for a second. So again, notice what they're claiming here. They're trying to, they're gonna make a claim about every set you could ever imagine or make. A, B, and C. Doesn't matter the context. We could be talking about numbers. We could stick some shapes in there. You could put pictures in there. Doesn't matter what the objects are in the set. So we're saying for all sets, A, B, and C, that could ever be created. We want to try to prove this, that if A is a subset of B, so these sets that I create, there's a couple restrictions or conditions here. First of all, A has to be a subset of B, so everything in A has to be in B. Again, I don't know what those elements are, and I actually don't care. It's even better that I actually don't know what they are. It's better that I don't care. They could be numbers, they could be whatever, it doesn't matter the context. So I'm trying to establish, as long as A is a subset of B, and B is a subset of C. So as long as everything in A is in B and everything in B is in C, so if you just hearing those two too, so if you got these three sets and you know everything in A is in B and everything in B is in C, then what do you know automatically? Good, you know automatically that A is a subset of C. And A is a subset of C. And hopefully, again, so hopefully that makes intuitive sense. It should make sense by definition. So like we said, we talked about the definition of a subset means if, so when I say A is a subset of B, so forget the whole proof now, but when I say A is a subset of B, I mean if X is in A, then X is in B. When I say B is a subset of C, I mean if X is in B, then X is in C. So again, it should be true that if X is in A, then X is in C. They should be subsets of each other. Good. So this at least makes intuitive sense. And even if you try to, we talked about in the last section that you could sort of draw out a Venn diagram, or we drew out a Venn diagram to sort of make sense. It didn't prove, but it made sense of some of the stuff we were looking at. This even makes sense in a Venn diagram, because in a Venn diagram, what I'm saying is I have A, and A is a subset of B, so B is some either same size circle or at least maybe slightly bigger circle. But B is a subset of C, so C is some circle around B. So this should work. A should be within C. It should be a subset of C. So at least not only in definition and an idea, but I mean, both in definition and idea, this should work. And so we want to go prove this. And again, notice the thing that we're doing here is we're proving this in general. So even when I drew that diagram for the Venn diagram for the sets, I didn't give any context. So picture wise, it should work. But we need to prove this in general, which means we need to use the definition, which means we need to do a direct proof like we just did in 6.1. So if we're going to prove something with subsets, then we need to make a proof exactly like we did in the in the last section. So this proof starts out so 3. You're going to start out with your if part of this. So we're going to suppose all of the if. And notice that's what she does there. Give me a second to figure out, do I want to rewrite this out as we're doing this? I'm going to rewrite it out just without some of us. So there's some statements there. So the usual thing that she does in a chapter where at the beginning of the chapter, the proofs have a little more of these extra statements that you don't need, but maybe help the reader or help you, more importantly, help you sift through the structure of the proof and how she's putting this together. And then as the chapter goes on, she starts taking out some of those extra statements. So I'm gonna go ahead and write this without some of the extra statements. So my proof. Suppose A, B, and C are any sets where A is a subset of B, B is a subset of C. And then what I want to get to, so this is what I won't write that, again, she does usually at the beginning of these chapters, but what I won't write is our goal. So our goal is to show that A is a subset of C. Good. Now, just like, again, like we were talking about in, what do you call it? In 6.1, once you have a definition, so once you have some sort of condition or relation or definition on, in this case, A, B, and C, that gives me some detail that I'm then gonna explain to the reader. Or I'm gonna use, sorry. So this one we don't even have to use. So suppose that there are any sets, and then we can say something like let X be an A. So X is some element in A. And because A is a subset of B then, so even if you didn't see the proof that she's laid out there, because X is X is a subset of A, or X is in A, and A is a subset of B, what do we know about X? Good. So by the definition of subset, that means that X is in B. So then X is in B. And that's just the definition of subset. So subset says if, in this case, if X is in A, then X is in B. So it automatically implies it. So definition of subset. So now we have that X is in B. So if X is in B, and we know B is a subset of C, what do we then know about X? Good. So then X has to be in C. And that's again definition of subset. And notice that then we have it. We started with X is in A. We now have that X is in C. So this actually, again, like a little bit like we were talking about on the proofs in 6.1, this is actually it. You don't have to actually say anything from there because we have the definition. We supposed X is in A, we showed that it's X is in C. Again, for me, I might just write something like the following here just to kind of give that victory to the reader, to let it be a little more clear to the reader. Therefore, A is a subset of C. And we have the proof. Good. All right, so then I think what I want to do is I think I'm probably actually going to skip to, well, yeah, I think I'm going to skip 2 for now so we can just get on to some bigger, larger, more formal proofs. So good. But this is what our proofs are going to start to look like. So I guess the point I was just thinking about that I wanted to make is notice that this is a subset proof just like we did in 6.1, but notice there's no algebra there. Because again, I'm going to start talking about sets in general rather than sets with particular, like, sets of integers that have such and such calculation or definition. So we're going to start talking about sets in general. So when we talk about sets in general, we have no algebra or anything else to refer to. All we have is the definitions for subsets, and we'll see we have the definitions for, what do you call it? Intersection, union, complement, set difference, etc. So our proofs are going to start to look like this, where we're just referencing, we're supposing elements are in one set, and then we're just referencing our definitions of intersection and union to kind of advance our arguments. All right, so a good example of this is actually number 6. And so I actually probably should have given y'all this. Well, no, I didn't want to give you this for reading because it's long, but maybe I should have still given it to you. But I want you to, let's take a look at number 6. And 6 is another fill in the blank proof. So I still want to step you up too. So this is a good subset proof. Let's look at a proof that involves unions, intersections, etc., and look at, formally how that plays out when my sets are not some algebra thing, when it's just A, B, and C being general sets. So let's look at 6. And for 6, let me kind of, again, take away a lot of their words there and just kind of focus on what we're proving. So what we're trying to prove is for all sets A, for all sets A, comma B, comma C, we're going to try to prove the following, that A intersects B union C is the same as, is equal to A intersects B union A intersects C. We want to prove that this set equals this set. So we also looked at, we looked at, what do you call it, proofs where we had to prove one set was equal to another. So remember that to prove one set is equal to another, you need to show that the set on the left is a subset of the set on the right, and then vice versa. The set on the right is a subset of the set on the left. You need to show they're both subsets of each other, because the only way for them to be both subsets of each other is that they in fact are the exact same set, that they're the same numbers or same elements at least. So that's where we're going to go with this. Is you'll see in the proof that she's set up, there's kind of 2 things. So in this proof, there are 2 things that we're going to have to do. We're going to have to show that A intersects B union C, so this is a lot of writing, is a subset of the right side. And then vice versa, we're gonna have to show that the right side, A intersect B, union A intersects C, is a subset of A intersect B union C. Proof kind of has two parts here. So again, we saw this with the equals proofs, the last proof that we did in 6.1. So be an expectation of that. What do you call it? These equals proofs, unfortunately, are just long proofs. They're literally two proofs in one. Usually you have two subset proofs in one go. Give me a second, make sure it's not. Okay. Let's see, what else did I want to say about this before we jumped into it? The other thing I wanted to get you guys to think about. So now, so this is going to be the overall structure of our proof. I want you to look at what the thing we're trying to prove, and tell me, does that thing that we're trying to prove remind you of any property, pattern, something that we've talked about in this class so far? Good. So hopefully, and maybe you don't see, but hopefully you do see that this actually looks pretty darn familiar to the following. So let's say and so if you go back to our statement logic, if I have something like P and Q or R, what is this equivalent to? Or what pattern or property do we know kind of works with that? Good. That's the distributive property. So we know that this is completely equivalent to P and Q or P and R. And then so they called this the distributive property, or we call this the distributive property. And when we were learning about this in chapter 2, I was mentioning that we have the same property for numbers, right? So if I do 5 times x plus 3, that's equal to 5 times x plus 5 times 3. So we have the same distributive property with real numbers using multiplication and division and addition. So we said that we called the distributive property, and then we discovered it's kind of freaking awesome or kind of crazy and cool that the same thing works with the and the or operator. But now notice that I'm saying essentially the same thing works, or I want to prove that the same thing works with the intersection and the union operator. And remember from what we were talking about last time and what we just mentioned too. I mean, so just look at the haunting similarity here. When I say haunting similarity, I'm saying actually they're exactly the same pattern. They're exactly similar. And is intersection or is union, like we were just talking about. And is intersection or is union. So this is literally the same pattern, the same statement. Just in chapter 2, we were talking about what do you call it? Logical statements. In chapter 6, we're talking about sets. But the same thing should work. There's the same thing works. So this is, again, we call this a distributive property. So we're saying the distributive property works for real numbers. It works for statements. It's now going to work for sets. That's kind of freaky. Maybe that means the distributive property is pretty freaking important in a lot of kind of realms and applications. So by the end of chapter 2, we got to saying that basically we call this a Boolean algebra. So maybe we're about to figure out or say that sets also are a Boolean algebra using intersection and unions. Maybe we're going to see that. So at the least what we're going to see out of this proof, or what we're going to try to prove, is that the same distributive pattern basically that we saw for and or works for intersection and union, which again, hopefully that makes not only intuitive sense to you, but like you look at it and you're like, okay, that should work, right? Because my definition for intersection is an and statement, and my definition for union is an or statement. So actually it should work because it worked for and or. So that's what we're gonna try to prove in 6. And so you'll see that she's got this fill in the blank proof for 6, but it gives you kind of the whole structure of how you do this. So I want to take a second to look at 6 because this then this will give you kind of all the different types of lines of argument that we're going to end up using in the proofs that we're going to see in this section. Because so on number 3 that we just went over, you saw sort of lines of arguments for subsets, and we're going to use some of those lines of arguments here because we need to prove that the left side is a subset of the right side and vice versa. But also, by proving this, we're gonna have to deal with the definition of intersection and union, which is something we also need. So what I'm trying to say is, we really want to look at this proof because this then is going to become a model for the proofs in this section. So what I'd like you guys to do then is I actually want you to try to fill in this proof to begin with before we get to it as before I come back with you on it or we get to it as class. So I'm gonna pause. I want you to pause, kind of really pour through this proof and see if you can fill in all the blanks. If you can't, that's fine, but kind of pour through this proof and see if you can fill in the blanks. All right, so you've had a chance to kind of look through that proof. So let's see if we can put this together. So what I'll have to do is just kind of catalog some of the answers here for part 1 and then part 2. So let me erase a little bit of this so I have some room. All right, so for part 1 here, so she starts out with the if part of this. The if part of it would be the first subset proof. So suppose A, B, and C are any sets. Actually, she starts there. So for the whole proof, we're just talking about A, B, and C being any sets. And then she starts out, let X be an A intersect B union C. And then we must show that, so what you would have had in this first thing, so we must show that X, and I'll write the whole part out, but X is in this A intersect B union A intersect C. So that would have been your first fill in the blank there. Now let's go back to, so she starts, but we know that this is where we're trying to get to, but we know definitely that X is in A intersect B union C. So by definition of intersection, X is in blank and X is in B union C. So notice this should seem familiar from what we did on that first reading assignment. So what you should have had here was X is in A. So basically, by definition of intersection, I can say then that X is in A and it's in B union C. Thus, X is in A, and by definition of union, it's then in X is in B or X is in C. I kind of want to highlight this. So she had the X is in B, you would have the or X is in C. So this would have been the fill in the blanks that you're doing. But notice what she's doing here. So right now I'm just kind of talking through this stuff, but notice what she's doing is she is starting with the hypothesis, and the hypothesis is some statement about a set that involves intersections and unions. And what she's doing is one by one breaking down those intersections and unions kind of from an order of operations from outside in, or kind of reverse order of operations, I guess. But from outside in, she's kind of breaking down those sets by definition. So every time she sees an intersection, she says X is in the one thing on the left and the thing on the right, right? And so the clever thing that's happening here is, again, without any context for A, B, and C, I can't use algebra. I can't use any tricks with what these objects are, definitions of the objects. So what I'm relying on is just the definitions of intersection and union. But that works because intersection always means and, union always means or. So we can use those to literally, I think about it, it's almost like you're unzipping this set into its logical, what it logically means, logical statements. So we're unzipping, so this original set that X is in A intersect B union C, now says X is in A also, and X is in B or X is in C. So she breaks that down into two cases. Case one, X is in A and X is in B. In this case, X is in A intersect B. And notice that A intersect B is one of the things that we wanted to say, that we wanted to see. Then case two, X is in A and X is in C. So what she's doing is, again, in my proof, what I have is X is in A and it's in one or the other. So she breaks this down into two cases. X is in A and X is in B. Well, that's awesome. Now, by definition, I have X is in A intersect B. Second possibility, X is in A and X is in C. In this case, X is in A intersects C then, by definition. And so then she says by cases 1 and 2, what we end up having then is X is in A intersect B. But we still have this or X is in A intersect C. Writing things wrong. A intersects C. And so the key is then that or I can retranslate that into what set operation? Good. I can retranslate that. So by definition of union, I can retranslate this. And so this is what you would have had filled in. X is in A intersect B, union A intersects C. So this is what you would have had filled in. So again, the clever thing that she does here, which is a thing that I think is really clever, so she starts with, again, in this case, the left side. She says X is in here, and then she unzips this, she unpacks this. So she says, well, intersection means and, so X is in A and it's in this thing. And then union means or, so X is in A and it's either in B or C. And then she, what do you call it? She makes two cases out. She rearranges those together, which we can actually do because of, she doesn't actually mention the reason here, but we can do that because of the distributive property with logical statements. That's actually what we're doing. So she gets all of this and then basically says, well, I can rearrange that as X is in A and X is in B, or X is in A and X is in C. And she can do that because we already did that with logical statements. So X is in A and it's in X is in B. So then, so we get down to this place where it's all logical statements, it's all ands and ors. And then what she does is she uses the properties of logical statements and the definitions of intersection and union to then rearrange this and zip it back up into this set statement. So she says X is in A and X is in B, and she says, well, and is intersection. So now we have this part. And X is in A and X is in C, so now we have A intersects C. And or still means union, so now we can stick a union between them, and voila, we have our statement. So she proves that if X is in the left side, it's in the right side, and she does it completely by breaking down the set into logical statements and then taking the logical statements and rebuilding them up into a set. And so again, the curious thing here is I think the cool thing about this is because there's no definition of the set, we don't have the advantage of algebra or definitions. We completely just use the definitions of what do you call it, unions and intersections, and we'll see, there are other definitions that we know. But we completely just use them in their logical statement form And the logical statements build up the sets. We actually don't need algebra. We don't even need to know what's in the sets. The logical statements themselves build up the sets. And that's the key to these proofs, is we're saying the logical statements themselves should be enough. Okay, so I've kind of said that 50 times, but hopefully that kind of strikes you, or at least you get why it strikes me, why it makes me so happy, honestly, so happy, and kind of think these are cool proofs. All right, good. And then she has the second part of this. So the second part of this is we got to start with this. So assume X is in here and then show that X is in there. Okay, so let me go through this. So I am going to have to, I have something planned for tonight, so I am going to have to leave at this point. It's a little after 7. So let me work through this, and then what we'll do is I'll have a second part to this video to kind of finish off some of the others. So we'll do some examples of these proofs. Now that we've done one of these proofs, we're filling in the blanks, but this is a pretty involved proof. Now what we're going to want to do is be able to build one of these ourselves. So we'll do that, but we'll have to do that in a second part. But let me finish off part 2 here. So this was part 1. Then what we can do is let me erase this for a moment, and we'll do part 2. All right, so case 2. Or no, sorry, not case. Wait, we did case 2. Oh, sorry, part 2. So she starts out by assuming X is in. So we're gonna, again, you didn't have to write this part, but we assume X is in this. By definition, so then she says, by definition of this union here, we can say that X is in A intersect B blank AX intersect. So A intersect B. So X is either going to be in there, but then this union turns to what word or what operator? That turns to or. So or X is in A intersect C. Good. And then she builds kind of 2 cases out of this again. So the first case is, let's assume that X is in A intersect B. In this case, by definition of intersection, X is in A and X is in B. Since X is in B, then X is in B intersects C by definition of union. So basically by definition of or. Here we go. So, but let me explain that line that she writes there, because so this is an important. When I say important, I'm saying more like this is a logical, not leap, but this is a logical line that you sometimes need to take, and I think it's not as obvious when you first read it. So let me just kind of emphasize that. So it wasn't anything you had to fill in, but let me emphasize it. So she goes on from here. So basically, part 1. Hold on, let me make sure this is still going. It looks like it just tried to shut off. No. Okay, it's still going. Okay, good. All right, so part 1 is basically this. And then case 2 is going to be that. But from here, she says, well, this means X is in A and X is in B. Okay, and clear enough. Intersection means and. So we have X is in A, but then what she does a clever little leap here. So notice that C is not part of this, but my goal though is to say that X is in A and it's in B union C in each of these cases. But C is just not there at all. So the first part of the proof, the first half of the proof, we had all three pieces. And so honestly, it was easy to construct what we had here because you already had all three pieces. But when you're looking at this part, this one little case here, you only have A and B. So how do you get to saying something about C? So what she's doing here is she's saying, well, if X is in B, so if X is in B, we can say that X is in B or X is in C. Now C comes out of nowhere. So why can we say that? And so what she's doing here again is clever because remember that or, for something to be true as an or statement, it either has to be in one or it has to be in the other. So this is that should be the little n symbol. So it either has to be in one or the other. So if X is in B, is it in B or C? And because of the definition of or, what makes or statements true, it is in fact, you can say X is in B or X is in C, even though C didn't exist in this case. In fact, you could say that if X is in B, you could say X is in B or D or Z or whatever you want to say, because whatever that other set is, or to be true just needs it to be in one or the other. So we can always say X is in B or X is in something else. And this becomes X is in B union C by the definition of or, by the definition of union. And I think to the order that she's going. Yeah, no, that's fine. That works. So in the first case, first of all, so again, X is in A and it's also in B union C. And then what she does in the second, so what I want to do here is I think it's much, like we can fill in the blanks, but I think it's much more important to really make sure we understand kind of her logical argument here and just kind of the line that she's taking. So in the second case, she says, in this case, by definition of and, so here in the second case, X is going to be in A and X is going to be in C. Okay. And then she uses X is in C to then make the same little clever logical jump. So she uses this to say, well, if X is in C, then I can certainly say that X is in B or X is in C because it is in C, and or just needs it to be in one of them. So again, you could staple anything you want here actually, and it would still be true because an or statement just needs one or the other to be true. And we'd already have one of them true. And X being in B or X being in C means X is in B union C. And so notice that in both cases, what we have is X is in A. Actually, let me. So in both cases, what we have is X is in A and X is in B or C. So both of these say X is in A. Oh man, it's still circled it wrong. Jesus. All right. So both of them say X is in A and X is in B or C, or B union C. So then what she finishes out after case 2, what she finishes out is basically saying, well, that means in either case, X is in A and intersect B union C. And then we've got the second part of that proof. So she does it in a very sentence driven kind of narrative wordy format. I, at least in trying to break this down, I'm not saying that this is in any way like this is maybe how you would write the formal version, the more formal version of this proof. But what always helps me is visuals, and so I'm trying to sort of make the logical connections that she's making in her argument to you, but I'm trying to do it visually. What do you call it? But this is what this proof would be. So we need to do proofs like this. So this is kind of like I said, the 6 is your first introduction to like, again, what we're doing, which is clever and cool, is we don't care about the context. We can prove these things simply from definitions and logical, but breaking things down into logical statements. So you take the sets, you break them down into a logical statement, and then you take the logical statements and you build them back up into the set that you need. So we can do it that way. And hers version is what it would look like, more statement driven. Again, this is not, I still would need to clean this up and make this a little more, organize this differently to make it formal, but this is how I would do it in a more formal, less wordy driven version. So one of those, you figure out whichever one you like, but this is what we got to do for this section. We got to be able to prove things like this, but put these proofs together on our own. So take hers as an example, and like I said, I need to get going, but I'll come back with the second part to this. So take hers as an example, and we'll come back and put together at least one or two of these proofs on our own. All right, I'll see you for the second part.